Good day. Welcome to the Physics Exercises channel. And today I will be discussing something called the Hohmann transfer orbit. So we're going to do an elementary calculation, but first we discuss what this is. Okay. And the Hohmann transfer orbit is an orbit for getting satellites from one planet to the other. Okay. So roughly the story is as follows. Let's say you have the sun here. Okay. And sorry, around the sun. Let me erase that and try a little better. So I will just write like this. So here we have the Earth. And roughly speaking, the Earth goes around the sun on a circular orbit. And I apologize if that's not quite circular. Okay, let's take some other planet. I don't know, Mars. Okay, so let's say Mars is here. Okay, and there's another orbit that's also on another orbit. Okay, so we're going to assume, although this is not true, right? So this is an assumption that I state. Okay, so Mars and Earth, circular orbits. It's almost true. I mean, of course, we know from Kepler that the orbits are elliptical, but the eccentricities are very small, so we can take them to be nearly circular for this problem. And what the Hohmann orbit does is if you launch a satellite on the Hohmann orbit from the Earth, let's say, okay, and you put it on an elliptical orbit. Okay, so let me actually, you know what? Let me give this a different color. Okay, so let's say, and the idea is that you put the satellite. Okay, so this is where the satellite is. Let me just abbreviate it as SAT. You put it on an elliptical orbit, and basically you give it a boost velocity at the start, and then you give it a thrust in the opposite direction of its motion when it gets to the Mars orbit. In between, you don't have to do anything because gravity does the job for you. Okay, so I want to emphasize this a lot, that so the orbit is entirely determined. So let me write determined by the gravitational force. Okay, so that's the beauty of it, that you give it an initial velocity here from the Earth, and then it leaves the Earth, and basically it's going to only be affected by the gravitational force of the sun. Okay, so there's going to be a gravitational force between the satellite and the sun. Okay, so let me indicate that in green. Okay, so this is a gravitational force, but it's entirely due to the sun. And the object will stay in orbit and arrive at the orbit of Mars. Okay, and you don't have to do anything in between. You just have to be careful about a few things. And the things that you have to be careful about is you give it the proper initial velocity, you give it the proper final velocity, because if you don't do anything once it gets here, okay, so if you don't do anything when it's at this point, it will just keep on that elliptical orbit. Okay, it will just keep on that elliptical orbit. So you have to give it an acceleration in the opposite direction to slow it down so that it will stay on the new circular orbit of Mars. Okay, so that's to get a proper Hohmann orbit is one, we need a boost velocity. Okay, from the Earth when we launch the satellite. Okay, two, another thing that you need is to slow it down once you get to the Mars orbit. And I will call that the anti-boost velocity. At the Mars orbit. Okay? And let's do some initial calculation. There's a third thing that you have to be careful about. And that's called the opportunity. Okay? The point is that this satellite obviously is going to travel half the period of this elliptical orbit. Okay, so let's call that t divided by 2. That's half the period of this elliptical orbit. And it should get there when Mars is, so it should get to this point here when Mars is here. Okay, so it has to be launched at the proper time for that to happen. Okay, so I will just write here, launch at the right time. Okay, so these are the conditions to be able to send a satellite from Earth to Mars using the Hohmann orbit. And now let us do some calculations, okay? So I'm going to derive formulas for the proper velocities. Okay, so I'm going to redraw it every now and then, okay? And let's see. So again, here's the sun, okay? Here's a circle, that's the Earth. Okay, and let's say here's the other planet, Mars. Okay, and these are supposed to be circular, which I didn't succeed in, but be that as it may. Okay, and let us calculate the velocity of the Earth to start with. Okay, and we know that the Earth experiences a gravitational force, and the magnitude of that gravitational force is g, mass of the sun, mass of the Earth, divided by the radius of the Earth's orbit squared. And this means that so that's actually a centripetal force. Okay, it points towards the sun, but it keeps the orbit in uniform circular motion under our assumption of a circular orbit for the Earth. Okay, and so based on this, we can do a little bit of rearrangement, and we see that, so if we cancel RE and cancel ME, we get that VE is equal to GMS divided by RE, and we have to take the square root. Similarly, and I'm not going to do this calculation, but we have V Mars, okay, and that's going to be GMS over RM. Let me just indicate, though, that that's what I mean by RE, the radius of the orbit of the Earth, and that's what I mean by RM, the radius of the orbit of Mars. Okay, if we compare these, we know that the radius of Mars is bigger than the radius of the Earth. Okay, what happened there? Just a second. Let me erase that silliness. Come on. I don't know what happened there, but yeah, whatever. Okay. Anyway, let me then write it here. I don't, let me try again. So RM is greater than RE. Okay, which means that the Mars velocity is actually smaller than the Earth velocity. Okay, so these are sort of initial conditions, okay? And we're going to do the following. So let me again draw a picture. So we will keep these two results in mind because we need a boost velocity, and the Earth already has this velocity, which means that our satellite initially has this velocity, but we need a boost velocity to put it on the orbit. Okay, so let's first calculate that. So let me actually redraw the picture. Okay, so basically I have the Earth, I have the sun, I have the Earth, okay, and here I have a circular orbit, okay, and here I have the orbit of Mars. And let me just indicate that with, so actually, so this is the radius of the orbit of Mars. And this here is the radius of the orbit of the Earth. And like I said, we are looking for an ellipse, right? So we're looking for an ellipse, which is roughly here. Okay. And what we know about this ellipse, okay, so these are all properties, well-known properties of the Hohmann orbit. What we know about this ellipse is that the sun is at the focal point of the orbit or the ellipse. Okay. We can also, let me actually just make this look a little better. We can also say a couple of other things. Namely, we can calculate that. So this distance here is Rm. This is Re. So we can also calculate the semi-major axis of the ellipse. In case we need it, and I'm going to denote it A as Rm plus Re divided by 2. Okay, so that's sort of just to characterize our ellipse. Okay, then we can calculate eccentricity and other things if we need it. Okay, okay. And now the question that we really have to work hard to calculate is the initial velocity when we launch the object at the Earth. Okay, and the boost velocity is going to be the difference between WE and VE. Okay, that's what we're going to call the boost velocity. And another thing that so that's actually the velocity at this point here at the Earth. And actually, it's going to go this way on this elliptical path. Okay, so if we get here, it's going to have a different velocity, Wm. Okay, and Wm is going to be higher than the Mars orbit velocity. So there we have to actually slow it down. But for both of those, it's sufficient if we calculate these two velocities. Okay, so these are the velocities at different points on the ellipse. Okay, so at the perihelion, which is, if the sun is here, that's what we call perihelion, and at the aphelion of the ellipse, which is here. So once again, this is the perihelion, and this is the aphelion. Okay, we want to calculate those two velocities. Okay, and we use two laws of physics. I will redraw the picture, okay, when it's needed. So again, sun, okay, and I would just draw the orbit here. Okay, I would just draw the orbit in red. So I'm going to try to draw an ellipse. Yeah, okay, something like that. Half an ellipse, actually. Okay, and what we need, and notice two things, that at this point and at this point, the velocity, okay, so WE, the vector associated with that velocity, is perpendicular to the vector associated with connecting the sun and the satellite. Okay, and this is also true here. Okay, so this is Wm. Okay, and like I said, Wm is the velocity that the object has while it's on the Hohmann orbit. Okay, so if you keep it on that velocity, we'll just keep going on that ellipse, and it won't stay at Mars. You have to, when it gets there, you have to slow it down from Wm to Vm, which we already calculated earlier. Okay, but now the question is how to calculate these two. Okay, and we're going to exploit two laws of physics. One is energy conservation. Okay, so energy conservation. That's an R, apologies. Okay, and the other one is angular momentum conservation. And these two conservation laws will furnish two equations, and we can go and solve for WE and WM. Okay, so let's do that. Okay, so the point is here that the satellite, once it's on the elliptical orbit, its energy is going to be conserved. Okay, what we mean here is the mechanical energy. That is the mechanical energy on account of its gravitational interaction with the sun. Okay, so let's do the first one. Okay, so let's write the energies in the two positions. And I'm going to denote this position 1 and this position 2, or perihelion and aphelion, perihelion being 1 and 2 being the aphelion. Okay, so at 1, our energy is mass of the satellite. I'm going to denote that by m, WE squared divided by 2 minus capital G mass of the sun, mass of the satellite divided by RE. Okay, and you know what? I'm going to erase my 1, okay, from here, and I'll just say that this is the energy at 1. Okay, and this is equal to the energy at point 2. Okay, and if I write the energy at point 2, I should be writing m Wm squared divided by 2, which is the kinetic energy of the object. Sorry, a mistake. It should be an m, not an e. Okay. Okay, like that. Minus G ms, mass of the satellite, which is small m, divided by Rm. Okay, so that's the energy conservation. Okay, so let me actually fix something else here, maybe a little fix up. Okay, so this is what we get from energy conservation, and I'll abbreviate that. Okay, and now we also have angular momentum, conservation. Angular momentum conservation. Okay, and actually it's the same expression. Oh, no, sorry, it's not the same expression. I will derive it. First of all, the angular momentum generically is given by R cross P. Okay, and R cross P we can write as RP sine of the angle between R and P. And this is where it helps that this vector here, which connects the sun and the earth, is perpendicular to the momentum vector at this particular point. This would not be true, for example, at an intermediate point on the ellipse, right? So here, your P is roughly that way, and your R vector is roughly that way. But at these 2 points, 1 and 2, luckily, we have this situation that theta is a 90-degree angle. So we can basically say R times P, which is equal to RMV in this case. Okay, so it's only true if theta is a 90-degree angle, but in this case, that condition is satisfied. Okay, so that's our expression for the angular momentum. But now we have to be specific. At this place where RE, we have RE and we have RM. So we see that the angular momentum conservation gives us RE MWE, and that's equal to RM MWM. Okay, and now we have to massage these equations and get a result. Okay, so first of all, let me write the two equations next to each other, and then we start working on them. Okay, so we can write m over 2 WE squared minus capital G ms times m divided by RE, and that's equal to m WM squared divided by 2 minus G m sun again, m small m, that's the mass of the satellite, divided by Rm. Okay, and let me work on this equation a little bit. So, okay, we have also this equation here, which is RE MWE. So I will work on both at the same time. Rm MWM. And let's say the first thing that we should immediately simplify is that the mass of the satellite disappears from all of them. Okay, and let me write, okay, so WM is equal to RE divided by RMWE. Okay, so that's one. This relates WM to WE. Okay, so we eliminated one of the variables, but we've completely eliminated when we write it in the other equation. Okay, so let me write the first equation in a slightly different form. I'm going to write this equation from which small m was already canceled as WE squared minus WM squared is equal to 2GMS 1 divided by RE minus 1 divided by Rm. Okay. Yeah. So that's our equation. Okay. So that's our equation. And let me write it a little bit nicer. This is Re, and that's Rm. And to get WE, for example, we would just, or WM first, I guess, is let's make this substitution, right? So we can say, let me get WE first. I think I like that better because that I can invert this. Okay, so I can write this is actually okay. So WM, if we square it, we get here 1. We get here 1 minus RE squared divided by Rm squared, and this is of course still equal to 2GMS, and these numbers. So let me actually write this as Rm minus RE times Rm. Okay, so this is all a little bit of algebra. Okay, and here on the left side, I can simplify as WE squared divided by Rm squared minus RE squared. And on the right side, I still have 2GMS Rm minus RE, and that's divided by RE and Rm. And here there's a square, which you don't see well, but you can cross the square. So I'm going to cross this square, and I'm going to cross one of the Rms because those two cancel. Moreover, we can actually simplify this because we can write WE squared divided by Rm, and this is of course Rm minus RE times Rm plus RE, and this is equal to 2GMS Rm minus RE divided by RE. And if you compare these two expressions, then we can cancel the Rm minus RE. And what we get for WE squared is 2G ms Rm divided by Re, and 1 divided by Rm plus Re. Okay, we can write it like this. Okay, so what we have, and now let's take that square root. We is equal to, okay, I'm going to write G ms Rm divided by Re. And I'm going to write this as 1 divided by the semi-major axis. And I still need a square root, okay? Because note that a semi-major axis is Rm Re divided by 2. Okay, so that's our result. That is our result. Okay, and now I don't want to redo this calculation because I don't have to for Wm. Okay, but if you notice that if I switch the E and M, okay, so these equations are symmetric. So I can switch E and M. Okay, here Re with Rm, E and M between these two velocities. So I can switch this M with to an E, this M to an E, this E to an M, this E to an M, and I can do that everywhere here as well. And if I solve that, what I would get is Wm is equal to square root of G ms Re Rm 1 divided by A. Okay, so that would be Wm. That would be Wm. So what we calculated here is, so if we now go back to our orbit, let's just remind ourselves that here's our elliptical orbit. And the sun sits right about here, okay? And I need a velocity here, which is We. And when the satellite goes through half the ellipse, it will have a velocity of Wm. But in order to keep it on the Martian circular orbit, you need to slow it down to Vm, which we also calculated. Okay, so here we take it from Ve and give it a boost, so it gets to the velocity We, then goes through the Hohmann transfer orbit, and here its velocity is going to be Wm, but you slow that down to Vm to stay on the Martian orbit. Okay, so that's basically the calculations that you need for the velocities. Okay, now there's another question though. Okay, and for this I have to make an approximate calculation here. Okay, and the other question is, what should the angle be? So I'm going to draw this again. Okay, so let's say here's the sun. Okay, and well, we'll have to say that, well, okay, let's do it like this. Here's the Earth, okay? And now I again draw my Hohmann orbit. Something like that. Here it should be perpendicular, sorry. Okay, and now I draw my Mars. Okay, so let me go to my Mars. Okay, so here's my Mars. But my Mars, okay, so I'm going to draw it in a more generic way, not the same place as the Earth is, not the same angle that the Earth is. Let's say that the Mars is, Mars is about here. Okay. Okay, and we're going to ask the following question, that what is this angle? Okay, so what is this angle theta? Okay, and then you can answer also what is the angle between Earth and Mars if you want, because you see that this angle here, so this is a straight line. So if I tell you what theta is, then 180 minus theta equals what I designated as alpha. Sorry, little mistake, let me erase. Is actually the angle between, so alpha is the angle between Earth and Mars. Okay, and now what do we know about these angles? Okay, so first of all, whatever, so the ellipse has a period. Okay, the ellipse has a period, so t is the period of the ellipse. Okay, and we will say that, well, we see that while it's on the Hohmann transfer orbit, you need half a period, because that's going to be the time available. Okay, so that's going to be the time available, half a period. Okay, and now we can use Kepler's law, Kepler's third law, to relate the period. We don't know this period yet. Okay, but we can relate the period to the semi-major axis. Okay, and let me do, so I'm going to do here an approximate derivation, but let me say that the other thing that I need to do is that, okay, Mars is going to go around its circle and arrive here. So Mars is going to cover an angular displacement of theta during the time t/2. And we want to calculate that theta. Okay. Yeah. Okay. So first, let us calculate the period of the ellipse, but this is going to be an approximate calculation, because I know the following, and that Kepler's third law can be derived from a circle with radius A, let's say. Okay, so we can say that I'm going to derive Kepler's third law because I don't remember the actual formula. So if I have a planet M, and they orbit in a circle R, okay, like that. So this is capital M. This is supposed to be capital M. And this is small m. So this is a small auxiliary approximate calculation. But we see that the planet, if it's going in a circle, its acceleration is v squared over r. So the centripetal force on it is mv squared over r, which actually is gmm over r squared. Okay, and then I can cancel the m. I can cancel one of the r's. And what I can also do is to write for velocity r times omega. This is not an entirely clean calculation. You can do this for an ellipse, but it's more complicated. Okay, so r squared omega squared is equal to gm over r, meaning that omega squared is equal to gm over r cubed. And you know that omega is the angular velocity, and the angular velocity is related to the period as 2 pi divided by t. So we can also make the following substitution for omega. And then we basically have Kepler's third, right? So we can also write that we could write the following, that 4 pi squared divided by gm times r third is equal to t squared. Okay, so this is what I derived for a circular motion, but I know, although the derivation is a little bit more difficult, that this is also true for an ellipse when the semi-major axis, you substitute the semi-major axis for the radius. So in other words, if I have a semi-major axis, and in our, now we go back to our case, the semi-major axis is Rm plus Re divided by 2. From this, we can calculate the period by saying 4 pi squared over gm a to the third is equal to t squared. Okay, so we have our period. Okay, so based on this, we have our period. Okay, so just take the square root. Okay, so this period that's actually how I think Kepler's third law is usually stated, that t is proportional to a to the 3/2, and the proportionality constants are given here. Okay, so we have our period. Okay, and if we are given that period, what we want is to calculate the displacement. Okay, so, and the point is that the displacement theta that Mars undergoes, Mars should undergo as we launch the satellite from the Earth, should be equal to the angular velocity of Mars times the period which we know already. Okay, and we also know that sorry, that's a mistake. The angular velocity of Mars is, well, we calculated Vm earlier, right? Let me erase that again. One mistake, sorry. So Vm t divided by Rm. Okay, now I just go back to our Vm because we calculated that earlier. That was one of the first things calculated, actually. So I gently scroll back. Where is my Vm? Where is my Vm? I know I calculated it. Here it is. Okay, GMS square root divided by Rm. Square root of GMS over Rm, rather. That's a better way to say it. Okay, so square root of GMS over Rm. Let's cube this, so we put this Rm inside the square root. Okay, and this is t. So this is our angular displacement. So basically what we calculated now is that the relative positions, here's the sun, again, here's the Earth, okay, and here's Mars, okay, and we actually calculated this angle theta, okay, so if you, alpha is obviously 180 degrees, or pi radians if you want, minus theta, okay. Actually, I was working in radians earlier, so let me actually erase that, and let's, so this is actually pi minus theta, okay. So this angle alpha is pi minus theta, okay. So the relative angle of the Earth and Mars should be pi minus theta according to this calculation, okay. Yeah, okay, so what did we do? We calculated everything that we can know about the Hohmann orbit, okay. So we calculated first the velocity of the Earth, the velocity of the Mars while they're in their respective orbits. We calculated the velocity we need to give to the satellite to get on the Hohmann transfer orbit. And we also calculated the velocity with which it arrives when it gets to the orbit of Mars. And we calculated an angle alpha, which is the relative angle of the Earth and Mars that they should be, so that the satellite gets there at the right time, okay? And basically, you can look at some interesting videos about this, but there's something called an opportunity window, or window of opportunity. And interestingly, that's about 2 weeks time. Okay, so there's a 2-week window of opportunity that you can launch a satellite, and if you do it properly according to these parameters, that satellite will get there and actually reach Mars. Yeah, okay. Thank you very much. Have a nice day.